Our next speaker is Henry Ems. Henry received his BS in Mechanical Engineering from the University of Nebraska-Lincoln, or UNL, in 2013. He went on to receive his Master's in Mechanical Engineering and Applied Mechanics from UNL in 2015 and is currently pursuing a PhD at UNL through research efforts in the Multi-Scale Heat Transfer Lab. In collaboration with the Center for Electro-Optics and Functionalized Surfaces at UNL, Henry currently performs drag studies on surfaces with femto laser surface processing to investigate drag reduction and enhancement. The title of Henry's talk today is Turbulent Drag Reduction/Enhancement in a 304 stainless steel rectangular channel functionalized with a femtosecond laser. Henry, take it away.
Thank you, and good afternoon, everybody. As Eric talked about, my presentation is turbulent drag reduction/enhancement in a 304 stainless steel rectangular channel functionalized with a femtosecond laser. All the work in collaboration was done here at the University of Nebraska-Lincoln, and my advisor is Dr. George Gogos here at the university. So to give you a little presentation outline, I'll go through a little bit of the background, specifically over some of the fluid mechanics that this covers, go through drag reduction in general, and what we understand right now. Then I'll build a little bit on somewhat of a background on femtosecond laser surface processing. I think a lot of people here, this will be a newer technique to them. So I'll kind of discuss how we do it, some of the strengths that we have for that. I'll go through the channel flow setup itself, and I'll talk about the loop I have, the pump that's being used, and some of how we get the measurements that we're doing. Then I'll move on into a verification, basically a test that we did to show that the system itself is running and that we're able to get reproducible data similar to what was done in previous literature. Then I'll get into a little bit more of the experimental side of this. So how we process these angled microstructures that we get, some of the parameters that we had, build on the drag testing itself, how we started with a super hydrophilic channel with angled microstructures, used a coating to make it hydrophobic, tested that, and then looked at kind of this plastron or air vapor layer lifetime and some of the drag information with that. Then kind of wrap everything up with the conclusion, look at some of my funding sources and the references that we have. So go forward. In 1823, Claude Louis Navier introduced the idea of a slip flow condition at the boundary wall. Now, this is different from what we typically learn in fluid mechanics courses. Typically, you learn at a stationary wall, you have a no slip condition, meaning you have zero velocity at the wall. Now, what Navier did was talk about the slip velocity. So you are getting a velocity at your boundary condition, which also means a slip length, which you can kind of see on the right. So essentially, the larger the slip velocity or the larger this velocity at the wall, the larger the slip length. And the slip length typically correlates to where I would have this no slip condition that I typically would have in fluid mechanics. So why is this important? Well, frictional drag in hydrodynamic situation, if you think of boats, and then with submarines, they're 50 and 60% of the drag is due to skin friction itself. So essentially, by being able to reduce the frictional drag that we have, not only can we get fuel savings, being more eco-friendly, increased flow rates for, say, flow through a pipe, and we can get increased speeds for shipping vessels or missiles themselves. So research in drag reduction has typically gone through several configurations. Some of the earlier ones were done with pipe flow, where you're able to coat the inside of the pipe and look kind of either at the pressure drop itself or similar flow rates. Then you move to channel and micro channel, similar ideas to pipe flow. You can also look at the velocity using micro PIV, then looking at concentric cylinders, looking at the torsion that's being done. External flow, which can look at a variety of surfaces itself, just whether flat plates, you can look at bullets, and then flow past free-falling bodies. Typically with these, you see you're looking at terminal velocity measurements, and they're typically spheres. So research has been done to show that superhydrophobic surfaces, the more superhydrophobic surface it is, the larger the slip length, meaning we have more drag reduction, and that you're getting fluid flow past this air layer that's present, or this plastron. And you can kind of see that in the bottom right figure with images B and C that's given. And then using a laser scanning confocal microscope, KEANS, here at the University of Nebraska, Lincoln, we're able to determine that when we have these femtosecond laser processed surfaces with microstructures, and we coat them using low surface energy materials, that this air layer comes up to the peak of the microstructures. So that's able to give us somewhat of a height of the air layer that we have. And then by monitoring the drag over time, we can kind of see how this slip length changes, which also will show kind of how this plastron degrades. Now, Lee, Choi, and Kim, in their laminar review back in 2016, which you can see this image on the bottom right, they talk about how if you just have a hydrophobic surface with image A, you get somewhat of a smaller slip length, and you don't have a vapor layer present. Now, if I go into B, where I have a vapor layer present, I can get the largest slip length possible. Now, one issue that we have with that is that these typically aren't stable themselves without some sort of external work being done. Now, you have seen that done with heating. If you heat to a Leidenfrost state, you can get this vapor layer, or you can inject bubbles. But then you have C, which is typically how our surfaces start, where you have microstructures that kind of trap this air or this vapor layer in, and you're able to get a larger slip length, but not as quite as much as having that uniform layer, but it's more stable over time, and you don't typically have to regenerate. Now, what we noticed with these surfaces that we did is we typically went from C, and then over time this plastron degrades and the air goes away. Well, we moved to more of an A with the microstructures, where you have a fully wetted surface and you're still getting some slip. Now, here at the University of Nebraska Lincoln, we've become kind of a leader in conducting research using femtosecond laser surface processing on metallic surfaces, and multiple applications that we've used them for. Now, some of the applications we've done wicking test, kind of discussing from the previous presentation that there was. Also looked at pool boiling, some anti-icing, microchannel boiling. So we've been able to use these for a variety of applications itself. Now, using in collaboration with the Center of Electro-Optics and Functionalized Surface and Electrical Engineering Group, we placed a focus on using these surfaces to create multi-scale structures for drag reduction or enhancement in turbulent flow scenarios. And now, the multi-scale structures themselves you typically see with things like the lotus leaf and a lot of things in nature. Now, using these coatings, we're able to get super hydrophobic surfaces. As you can see on the far right, of these steel. It's a powerful method for fabricating multi-scale structures. Now, one thing that's nice is we're able to take this by processing with the laser. We get the multi-scale structures. As I talked about earlier, you're able to get microstructures, typically pillars, though we have gotten spheres before too. And we're able to get nanostructures on the surface, which make them very ideal for both wicking with super hydrophilic surfaces and or non-wetting surfaces for super hydrophobic surface. We're able to laser process almost any material. We've done anything from stainless steel to Inconel to titanium and even glass. These structures are permanent, they're not going to change over time, and that we're able to basically make these without having any kind of contact with the surface itself. The laser that we're using right now is a coherent Austrella titanium sapphire femtosecond laser. Right now it's capable of producing 6 millijoules of power, 35 femtosecond pulses with a 1 kilohertz repetition rate, with the wavelength about 800 nanometers. And like I talked about before, we're able to produce multiple types of structures. We can have surfaces that are below the normal, smooth surface and how they start. We can have above surface growth mounds where these kind of pillar-like structures protrude above the original surface. We've got spheres, ellipse lines, which kind of look like wrinkles in the surface itself. And then we've also done chemical analysis to show that we're not getting any kind of foreign materials in the nanoparticle layer other than some oxides that have formed from the original substrate. And then using 3D confocal laser microscope here at the university, we're able to characterize the surface and kind of get a topology to get microstructure orientation, the height, and then the height above the normal or below the normal surface and how we start. So the channel flow setup. So the channel flow setup itself was designed to measure the pressure drop and flow rate over a rectangular cross section. And then we're able to change basically the microstructures or the coatings that we use in this channel using 4 different plates. Now, at the time, we used stainless steel, but we would be able to incorporate other type of materials in the future. A ground force pump that we use, we can pump purified water, 0.2 micrometer filtration through the loop itself, up to 16 gallons per minute. As you can see the pump on the far right. The volumetric flow rate itself is measured using a TRG Sabra TRG standard turbine flow meter. And we have a variety of those depending on the flow rate, and we're able to get about 1% accuracy as far as that measurement, and then a multitude of omega differential pressure transducers to measure the pressure drop along the test section itself. So the test section, as you can see in the bottom right, we're measuring the pressure drop over 45 centimeter in length, 4 centimeter wide rectangular channel with 5 millimeters tall. So it's a lot wider than it is taller. We're able to get the pressure drop over that specific area. And right now we're testing, we can test Reynolds numbers from 8,000 to 37,000 right now. So first thing we did, we went through a verification just to show that we can get reproducible data. So looking at HeartNet and some of the work that he did in previous years, he compared varying channel flow scenarios and the friction factors that they got and how they were typically in line with the Colebrook equation itself. So we're able to calculate the hydraulic diameter and the height of the channel. We know the width of the channel. Using the area, we can get the mean velocity itself. We know density, we measure the pressure drop, and we know the length of the test section. So overall, we're able to calculate out a friction factor from the measured pressure drop and volumetric flow rate. So, and as you can see on the far right here, the red box shows kind of the area that we're testing, and then the solid black line on the far right for the turbulent section shows the Colebrook equation on the, there. The far left would be more for laminar, where you see this difference depending on the geometry of the channel. As I talked, so we used multiple sets of plates to check the repeatability of the system itself. 2 runs were done for each set of smooth plates. We started at the lowest flow rate that we could get, around 8,000, and we went to roughly 13,000 Reynolds number using the same pressure differential. So we didn't have any issues switching out any kind of measurement devices. And then we did these over multiple assemblies, and for both set of smooth plates, we were able to get reproducible data that was in agreement with the Colebrook equation that you saw HeartNet in the previous slide use. Again, so what do? We took these smooth plates that we had processed. We processed them to get angle microstructures that were super hydrophilic to start, and then using a coating, we're able to make them hydrophobic, non-wetting, and use them in this channel flow setup. So we use 4 stainless steel, 304 stainless steel plates to form the channel test section. You have 2 on the bottom that are 4 centimeters wide by 45 centimeters long, and then you have even the side of the channel themselves were laser processed. The laser processing was done on the 304 stainless steel plates to form angle microstructures, which you can see on the bottom left image, which mimic those that we found on shark skin. And that we're able to, by angling the laser itself, that's how we get these kind of 35-degree angled microstructures that go in the direction of the flow. The peak to valley height of the structures, as far as the surface, as far as the liquid speed, was 36 micrometers, and they are 17 microns below the original surface. So you are taking some material away. Now, after testing these in the wicking or superhydrophilic wettability, we coated them using a fluorinated silane, a low surface energy material, to make them hydrophobic. And that was done using evaporative deposition. The figure on the bottom top right shows kind of the channel flow setup itself, the loop, where you have the pump, the pressures that are measured, how we control the flow rates, and then through the test section, and then the temperature of the water itself is monitored, though it doesn't change much over time. So after testing the smooth unprocessed plates, we processed these via FLSP to get the angle microstructures. Originally, they are superhydrophilic after processing. So if you were to put a droplet, it wicks or expands over the surface, kind of like you would see with a porous material. So we put these plates into the channel. The experimental data was obtained twice, 2 runs each, and then we had 2 different assemblies to show repeatability. As you can see on the image on the far right, the black would be the superhydrophilic. The red itself is previous smooth data that you would have seen in the Colbert verifications. We saw a increase in friction factor with respect to the smooth surface at the over the whole range tested, with about 10% increase at the highest Reynolds number that we tested. We do adjust the height for a valley-to-valley distance that you can kind of see on the bottom right. One thing that's different with this is you see with Moody, with previous work done by the Moody chart, in that they build their roughness up, whereas in our case, we are technically taking material away. So we're trying to get the base of the structure would be basically where the valley is. So we are changing for how those microstructures are, and then the depth that they're taken out of the surface. So after superhydrophilic testing was done, the surfaces are coated using a fluorinated silane and evaporative deposition to transition these from superhydrophilic to hydrophobic. So, and drag reduction was shown over the total range of Reynolds numbers where we had this plastron, which was early in the test itself. As you can see in the top right figure, we show drag reduction, and then kind of as the Reynolds numbers increase and as time has increased, you see this plastron degrade towards from the open green triangles to the closed green triangles. And then we go back through and run the test again without changing anything in the setup itself. Now we see that the second run itself falls slightly below the superhydrophilic. So that would show kind of what I talked about in the background, where you still have a hydrophobic surface, though that plastron and air layer is gone, you're still getting a small slip length. So that's why the data for the hydrophobic surface falls below the superhydrophilic. So as we talked about, using a Keyence microscope, we're able to get that the plastron itself is roughly at the tips of the microstructures, and so getting the height of the channel or the wetted area, we go from the peak of the microstructures to the peak of the other microstructures on top, and that's how we adjust that. Now, as the plastron degrades, we evaluate it from a fully wetted, so an HVV, height valley to valley, as I talked about in the previous slide. So for the first 4 data points where we saw a plastron, we get roughly a 4% drag reduction with respect to the smooth surface. Next, we go through drag testing for the plastron lifetime. So as I talked about, as we increase the flow rate or increase the time, you see this plastron or that air layer go away. So what we did was we kept this constant at a Reynolds number of 9,000, and we monitored basically the friction factor over time. So what we should see is the largest drag reduction at the start, and then over time, this friction factor decrease until you get almost to the superhydrophilic. As I talked about in the previous slide, the hydrophobic should fall slightly below the superhydrophilic because you still have the wettability effect despite both surfaces being fully wetted. So we kept the Reynolds number constant at 9,000. Originally, we saw an 8% drag reduction in the friction factor at the beginning. And then at later times, as the plastron starts to degrade, or roughly around 10 minutes, you see this shift towards fully wetted, where we use HVV to calculate the friction factor. And you see that fall just below the super hydrophilic at Reynolds or at times 60 minutes or greater. And then we modified the channel to get a little acrylic viewport so that we can watch this plastron degrade over time. And it's a little difficult to see here, but you are able to see somewhat of an air layer that is there, that is present in this hydrophobic channel. So to kind of wrap things up, we use 304 stainless steel plates, process them using femtosecond laser surface processing, or FLSP, to get angled microstructures that mimic those on shark skin. So for a super hydrophilic or a wetting surface and a wetting rectangular channel, with these angled microstructures, we measured drag enhancement or an increase over the total range of Reynolds numbers tested, with 10% drag enhancement at the highest Reynolds numbers tested. For a hydrophobic channel, with angle structures, we're able to get drag reduction for the Reynolds numbers where we did have a plastron present. And then as the plastron starts to degrade and fully wetted, you see the friction factor shift to the super hydrophilic. Though it is important to note that the friction factor does not cross or come in contact with the super hydrophilic value. You still have this slight change in wettability that accounts for the small decrease in friction factor. Some of the acknowledgments, Office of Naval Research for their help with this, the NASA Nebraska Space Grant Fellowship, which helped me this last year. And then the research itself is performed in part to a Nebraska Nanoscale Facility, National Nanotechnology, Coordinated Infrastructure for Nanoengineering Research Core Facilities, which is supported under an NSF award. Some of the references I had, as I talked about. And then I'd like to open this up to any questions.
Thanks very much, Henry. Let's see. Let's go to some questions. Okay. Let's see. We have a question on, have you evaluated this for biocompatibility with in-cabin applications?
So actually, not this specific work, but we have used FLSP on silver for heat exchangers and work with NASA. So typically when we do bio surfaces, we want to use silver. So this I haven't specifically, though we've used FLSP for that.
Okay, thanks. Okay, I'll ask a question. So what are your next steps going forward?
I'm actually in the process of making new surfaces. I built a super nice evaporative deposition chamber to deposit these in vacuum to get a little bit better coating. I've been able to get roll-off angles less than 2 degrees. And so I'm testing those in both the turbulent and laminar flow ranges. So I'm really excited to get the results on that in the very near future.
Okay, very nice. Another question off the chat. Was the water degassed prior to testing?
No, but I do have needle valves, or not needle valves, a bleeder valve available to get rid of air that is in the system itself during. I have some issues with degassing at the height of my building itself. I can't get the necessary pressure line to degas like I want.
Okay. So just to make sure, to clarify, so the degradation you were getting was the plastron degradation. It wasn't hydrophobicity degradation.
Not necessarily, yeah. So it is the vapor layer itself going away. Now that does have some effect on the wettability itself, though the surface itself isn't changing. So the coating in that is there.
Okay.
You will have a little bit more wettability as that plastron goes away.
Okay. So just as an FYI off the chat, there was some work years ago that showed that shark skin-like topography has microbe-resistant characteristics. Oh, that's interesting. So you may
Yeah,
be
there
able
is
to,
a lot of work that was done shark skin before. For the most part, they were using acrylic work typically, and you're more looking at like ridges necessarily.
given the femtolaser capability for geometry, you may be able to exploit topography for enhanced microbe resistance. I mean, I'm not familiar with the femtolaser. Is this a unique capability in the nation here with this femtolaser?
The University of Nebraska is one of the leaders as far as America goes.
Yeah.
There are other there is some work foreign outside of the U.S., specifically in Europe and China, and then you are able to there is industrial lasers available too. So as far as the United States goes, the University of Nebraska is one of the leaders in femtosecond laser processing research.
Nice. Okay. Doesn't look like we have any more questions at this time. Well, Henry, thank you very much. It's fascinating.
Thank you, guys.
Yep. So